Okay, we're going to take a minute here and look at three different bones of the skull that are made of more than one kind of bone during their development, but fused together as one piece as you grow. They are the sphenoid bone, seen here, the temporal bone, there we go, seen there, that's the right side, and then the occipital bone that goes underneath the skull. This is the back of the skull and the foramen magnum there. So all three of these are made from different parts of your developing skull: dermatocranium, neurocranium, and splanchnocrinium. So first of all, we'll talk a little bit about the sphenoid bone. The sphenoid, part of the sphenoid called the allosphenoi, move the spring out of the way, is found right here on the side of the skull, and that's derived from the splanchno-cranial component. You recall that both that and the incus and the middle ear bone is derived from palatal quadrate. So anyway, that's from part of the splanchno-cranium there. From underneath, when we look at the sphenoid, the only part of the sphenoid we really see are the pterygoid processes here and here on either side of the nasal openings right here. These are part of the dermal skeleton, part of that palatal series of dermal bone. The remainder of the sphenoid bone is found on the inside of the skull in here. Where the pituitary rests, and this region right here in the floor of the skull, and there's the lesser wings of the sphenoid there. So all of this part down here in the base of the skull, across here, and right in the very center of the sphenoid, right in the center of the sella turcica of the skull, right there, all that is endochondral in its origin. It's part of the neurocranium right here. The ethmoid is found just in front of it, so this is sphenoid right through here, and then it makes contact with both the otic capsules back here and the occipital back here. Remember, that's all neurocranium. The ethmoid, the sphenoid portion in here, the two otic capsules of the temporal, and around the foramen magnum, all that region of the occipital bone. That's all neurocranium in there. So here's a model of the sphenoid as a separate piece here. So all this middle part right in here, right in there, that's going to be neurocranial. These portions right here that hang down, these are the pterygoid processes to either side of the nasal openings, which would be right there. That's dermal bone. And then only this very outside part right here and over here is derived from splanchnocrinium. So that's a composite bone made of three different things. Same sort of thing going on here with the temporal bone. Most of the flat part of the side and the zygomatic arch going up right here, all of this is derived from a dermal bone. The splanchnocrinial component would be the styloid process, which hangs down right here. It doesn't show up on the skull there or on this skull. So we don't have a good styloid process. Let me get one. Here we go, on this skull right here. It's a very prominent process hanging down underneath the temporal bone, right under the ear opening right there, this long pointed projection right here. So that's the styloid process right there. That is derived from splanchnocrinium. And then finally, we mentioned earlier, all this area right here of the temporal bone, we call it the petrous portion of the temporal bone because it looks like a rock outcrop on a hillside or something. But anyway, that's the otic capsule region. That's from neurocranium. So we have this neurocranial portion in here in the floor of the skull, a large capsule there. We have the dermatocranial component out here, and then we have the styloid process, which is splanchnocrinium. Finally, we have the occipital bone, and the occipital bone, you can see the suture lines right along here, suture lines that go around and then down into here, all the way up to there, way up in underneath of the brain and the skull, and comes back in to either side along here. So this area around the foramen magnum, all of this around here, all of this is endochondral. This is from neurocranium. And then just a small amount right up here is dermatocranial in origin. There's no splanchno-cranial component to the occipital bone. So here's the model piece here. So all of this area right here would be neurocranial, and only this portion up here along the suture line, right along there, would be dermatocranial in origin. Now briefly we're going to go back and look at the head skeleton, the lamprey and the shark and other fish just for a little bit to give us some perspective across the vertebrate lineage. We didn't see any cartilage at all down in the urochordates and cephalochordates, so we first see it in the jawless fishes. This would be a jawless fish, and the only components we have here, well, we have 4 different kinds of cartilage. Out here in the front, around the mouth, that circular mouth of a lamprey, we have what's called an annular cartilage. An annulus is just a ring, so this is a ring of cartilage. Then associated with the brain region up here, we have neurocranial cartilage, or simply cranial cartilage is what it's usually referred to as in the lamprey. In the tongue, there's a lingual cartilage. Lingual cartilage in the tongue of the lamprey, which we don't see then in other vertebrates. And then finally we have this branchial basket. Branchial basket cartilage. So that surrounds the gills. If we were to draw the gill openings in here, they would go in sequence along the side of the head, something like that. There's usually 7. I got 6 in there somehow anyway. 7 gill openings on the side of the head of the lamprey. So these are the cartilages you find here. Now we're going to compare this to the shark. Now, the arrangement of things in the lamprey is such that it's assumed that some of the most anterior pharyngeal cartilages form the jaw component, but it's a little hard to tie in terms of having any fossil evidence linking that to the jaw of the shark. But let's look at the shark next. In the shark, there's a neurocranium, a large chunk of cartilage surrounding the entire brain. It's a fairly large structure giving shape to the top of the head of a shark. So that's all neurocranium up there. I'll just write in the middle of it here, neurocranium. A big block of cartilage. It's solid, not divided into pieces, is what I mean by solid. It's kind of uniform. But the upper jaw is not part of the brain case of the shark. Remember, in the ratfish, the upper jaw is fused to the brain case. But anyway, this upper jaw part right here, remember, is the palatoquadrate. And the lower jaw is Meckel's cartilage, part of the first visceral arch, the upper and lower jaw of the first visceral arch. There. Next, the hyoid arch is in blue in my picture. This cartilage right here, need space to write. Right here is the hyomandibular. Hyomandibular cartilage. Below that, this is at the corner of the jaw, by the way, where the palatoquadrate, Meckel's cartilage, and hyomandibular, they all kind of meet right here and forms that joint of the jaw in the shark. Below that, underneath here, is what we call a ceratohyoid cartilage. And then in between the right and left ceratohyoid, there's a bridge of cartilage going across there we call the basihyoid. cartilage. So hyomandibular, you have two of those, two ceratohyals coming around, and then one basihyal joining them in the middle, just behind the middle of Meckel's cartilage in the front. So that's the hyoid arch, the second arch. After the second arch, we have a series of what we call branchial arches. So the first branchial or gill arch in here has 1, 2, 3, 4, 5 components as you go from the bottom center to the top above the gill over here. So we're going to name these. The first one is the basibranchial. The first basal cartilage of the group. Then just above that, it's called a hypobranchial. Hypobranchial cartilage. Next above that is a ceratobranchial. Ceratobranchial is the main support for most of the gill in the shark. Above that is an epibranchial. And then finally a long pharyngobranchial that points backwards. So this arch-like component that starts in the middle and goes around to each side, supporting the gills on the left and right side, starts with a basibranchial in the middle and in the front, and then hypobranchial, ceratobranchial, epibranchial, and pharyngobranchial as you go around that arch, the gill arch structure from base to top in there. So this is considered the first arch, the mandibular arch with the palato-quadrate and Meckel's cartilage, then the hyoid with hyomandibular, ceratohyal, and basihyal, and then the branchial arch, the first of usually 4 branchial arches back here, 4 or 5, and they run from the basi, hypo, cerato, epi, pharyngobranchial cartilages. Okay, we're going to take a minute now and talk about the bony fish skull of the bony fish. We've done this before. We've looked at the bowfin skull before. Its outer skull there is all dermal bone. There's no dermal bone at all in a shark. No dermal skeleton at all. It's all neurocranium and visceral skeleton in there. But here we have all this dermal bone laid down underneath the skin to make up most of the skull of this. There's a little bit of neurocranium in here, and we'll see if we can focus on this. Right in here, right in the middle, right in the floor of the skull, right along there, is neurocranial bone, right in there. And there will be some visceral, visceral skeleton supporting the inside of the hyoid arrangement in there, but not very much. The gills have been removed, so we're not going to see that support system in there. But anyway, the rest of this out here, this is all dermal bone on the outside. Polypterus would be very similar to this. It has a more isolated neurocranium to the inside, but the outside of the skull looks pretty much the same as this, all well plated with dermal bone around the head shape and the gills and the operculum. Once we get beyond the amphibians into the amniote groups, we start to see some different arrangements of the skull that are described as either anapsid, synapsid, diapsid or euryapsid configurations that have to do with the presence or absence of openings behind the eye. Here's your orbit, the eye right here, and in the anapsid skull, there's a lack of post-orbital fenestrae, is what we call them, post-orbital fenestrae. There could either be a superior one along this suture line or an inferior one down in here. So anyway, it's above or below this post-orbital bone and behind the eye. So let's look at the examples then. The anapsid condition is present in the earliest fossils, the oldest fossils of reptiles in the fossil record. So that's considered the primitive condition, that anapsid condition with no post-orbital fenestrae at all. Now our next example, bring it up here, diapsid skull with two openings behind the orbit, one above and one below that post-orbital. So there's the eye. This is the diapsid condition, two openings, diapsid. The crocodilians, dinosaurs, birds, snakes, lizards, all thought to be along this lineage right here. We'll take a minute a little later and look at some examples of diapsid skulls with the two openings back there. Next example. The synapsid skull lacks the superior opening behind the eye, as the inferior one. It's thought that reptiles that took this direction in the fossil record were ancestral to mammals, and all mammals are considered synapsid. They have this one post-orbital fenestra just below, just positioned like this with respect to the neighboring bones. That synapsid condition, the post-orbital fenestra, is the lower opening. Now an extinct lineage, what was known as euryapsid, the euryapsid skull condition, had the superior fenestra, an opening above that post-orbital bone, but not below it. So that's the fourth condition. So you either have no post-orbital fenestrae, you have two in the diapsid, one above and one below, you have the synapsid condition with just the lower one, or the euryapsid condition in some extinct reptiles, just the superior opening. All right, we're going to look at a few examples of diapsid and synapsid skulls. We do not have any anapsid examples. That would be in some early fossil form of reptile we don't have here. The turtle skull is technically anapsid, but it's thought to be derived from a synapsid type of ancestral lineage, according to some of the more recent fossils of older turtles in the fossil record. So anyway, first of all, the alligator skull shows a classic diapsid condition. The orbit, the eye is right here, so behind the orbit we find a superior and an inferior fenestra or opening in the skull there. So that's the classic diapsid condition. Also in the tuatura, this is not an actual tuatura skull, this is a model, a replica. But anyway, this would be the orbit right here, superior fenestra, inferior fenestra, both very large openings and still very much intact. This would be allied somewhat with our snakes and lizards, but also very similar to what we see in many of the dinosaur fossils. Now, when we get into the snakes and lizards, they have what's called a modified diapsid condition, where there's the loss of either the lower member or the member that separates the two fenestra, or a posterior opening in there. So there are a number of ways that diapsid condition might be modified in some of the reptile groups and certainly in the birds. Here's a modern lizard. It's orbit right here. This is a monitor lizard. So behind the orbit we have an opening here, and above we have one there. So this is the diapsid arrangement. There's a little gap here between the eye and this posterior fenestra, and that posterior fenestra is not completely enclosed below. We've got the lower jaw across here, but we don't have any of the upper cranial portion bridging across there. It's even more extreme in snakes than what is seen here in this lizard example. So that's another diapsid example. In the birds, bring this bird skeleton over here, maybe we can look at it. It's kind of encased, so it's a little hard to see, but it doesn't look like there's anything going on behind the eye. The eye is very obvious, and what there was of any diapsid condition has been modified to the point that you can't tell any longer. So we've got the side of the skull is pushed out more. The brain is enlarged more to accommodate some of the features there. So anyhow, we really don't see that diapsid condition at all in the bird. That post-orbital fenestra, what there was of it is kind of fused with the whole orbit space. Now on to synapsids. This is a deer skull, and we have a nice orbit here. And behind the orbit, we have a complete bridge separating it from that inferior fenestra. There's no superior fenestra up in here. There's just this one down below right here. So that's the classic synapsid condition. It's very common for us to lose this separation between the orbit and the postorbital fenestra, right there, that inferior thing. And here we see it in a dog. So here's the orbit here, and there's not that same bridge when you compare it to the deer there. So we don't have this across behind the eye. We just go directly into that inferior postorbital fenestra there. So this is the synapsid condition. It's also that way on a cat. It's even more extreme in a rabbit, where you have a bigger orbit compared to everything else. You really lose the effect of that synapsid condition. In humans, we have a good orbit, and we have a good zygomatic arch, is what we call this, that separates the opening from the outside in humans. Here on the screen we have two illustrations that compare the crossopterygian fish, this would be Eusthenopteron here, to the labyrinthodont amphibian, that would be Ichthyostega. So that's the comparison we see here. And the skull bones, the dermal bones on the roof of the skull, have a lot of parallels. You can sort out equivalent bones, frontal bones, post-orbital bones, jugal bones under the eye there. So anyway, a lot of the plate arrangement that you see in the crossopterygian is not that different from a labyrinthodont amphibian, the Ichthyostega. A lot of similarities here in that. Also in the primary palate, the arrangement of the bones, you see this main central element, these long extensions down this way, and the plates arranged around the margin. So there's a lot of similarities still in the primary palate and in the dermal roof bones in these two groups. That just show the similarity of this ancient fish group to the earliest tetrapod groups there. Here's another example from the web page showing another important trend or feature that we should make note of. There's a reduction in the number of bones that we see in the different taxa as you move from the more primitive earlier forms to the later forms. So early synapsid, this would be a reptile that is, or maybe an early mammal in the fossil record. So we have a lot more dermal bones forming the upper jaw and lower jaw especially. But anyway, as you move toward more modern mammals, the generalized mammal example down here, we usually have a couple of upper jaw, the maxilla and a premaxilla up here, and only one dentary bone. It's not several bones together, and there are not as many dermal roof elements as we see in the early synapsid form here. So that's considered a general trend from your earlier mammals to your later mammals, a reduction in the number of bones that make up that dermal skull. Next, we're talking about primary and secondary palate. Primary and secondary palate. We've already discussed this some. The brain is separated from what's called an oronasal cavity. So you don't have separation of nasal and oral cavity. You just have one space in there if you're a bird or, most other lizards. Anyway, a lot of different things have this condition where here's your brain, and this is an oronasal cavity down below. A common space, this just happens to be a cut section, so that's the jawbone on one side, that's the jawbone on the other side. This is upper jaw, so our teeth would be here, and that cavity would be there. In mammals, and to a lesser extent in turtles, and even a greater extent in crocodilians, we have the formation of a secondary palate that grows across here that separates the nasal cavity from the oral cavity. And of course your brain's still up here, so your brain space inside your skull, then the nasal cavity, then the oral cavity. There. So if you're a bird, a lizard, a snake, an amphibian, you don't have this separation here. This is the primary palate. This is a secondary palate. So not everybody has that secondary palate. It's in mammals, it's in crocodilians, and to a lesser extent in turtles. Let's take a quick look at those three examples. I went ahead and drew in here the example of something that would have the nasal openings enter directly into the roof of the mouth in the front. So most lizards and birds, snakes, most reptiles, and their associated groups would fall in this category. The turtles have a little bit of a palate separating the nasal openings from the oral cavity. So just about, if you can imagine having your opening to your nasal cavities not all the way in the back of your mouth, but about halfway up in the roof of your mouth, that's what we see in the turtles. So they have nasal openings up there above, and then that connection goes through a common channel separated by a secondary palate for a short distance, and then enters the oral cavity here. The crocodilians, they have their nostrils way up here in the front, and they have a long secondary palate extending way back toward the back of the mouth, so that their opening between their nasal passages and their oral cavity is way back here. And then finally, mammals do basically the same as the crocodilians. They don't have as long a snout as crocodilians, but we have the same pathway. So we have nasal openings way up here in the front, and goes through the nasal passages, and then the air enters into the pharynx way back here. So these three have secondary palates. Separating the oral and nasal cavity. Now, in a turtle, what's behind here, that roof of the mouth there, would be a primary palate, as would be right here in these animals. Most reptiles and birds and all that. They have, between their brain case and the oral nasal cavity, a plate of bone there. That would be the primary palate. So primary palate here, primary palate behind the opening right here, secondary palate in front of it. Secondary palate here, secondary palate there. And here is an illustration of how the secondary palate forms in mammals. We're going to separate the oral cavity below from the nasal cavity above. We're going to see bone grow inward from the maxilla, slightly from the premaxilla, but mainly from the maxilla. And as it comes together, eventually it forms these nice flanges that are dividing the oral cavity and the nasal cavity. And eventually they close in together. And the palatine bone also becomes incorporated at the very back part of the hard palate, that bony palate, that secondary palate that forms across there. So it's mainly a growth of the maxilla, partly palatine, to a much lesser extent that premaxilla, which is really not expressed as a separate bone in humans, but most other mammals it is. Now our final topic on the skull, we're going to deal with the formation of the middle ear bones of mammals. Remember that having three middle ear bones, malleus, incus, and stapes, is a unique arrangement in mammals. We're going to start by looking at the expression of the hyomandibular cartilage in the intermediate forms. Hyomandibular cartilage, remember, is at a point where the palatal-quadrate and Meckel's cartilage come together in the shark, forms a large block of cartilage, and articulates with both of these other skeletal elements at the jaw joint, that hyomandibular cartilage. So next, in the amphibians and some primitive reptiles, we're going to see that hyomandibular move to a position between the dermal bone. Remember, the shark doesn't have any dermal bone. There's nothing coming around the outside of this, no dermal bone here. So anyway, it's going to find itself, the hyomandibular, between the neurocranium and the dermatocranium. And that's our next picture here. So this is simply described as early tetrapod in my illustration here, but out on the outside in white we have dermatocranium. Here's the neurocranium, the floor of the brain case developing here. And there's that hyomandibular, only now we're going to refer to it as a stapes, also known as a columella. Columella. So that's an intermediate state, but it's not really all that functional as a middle ear bone. Here we are a little bit later in an amphibian. Tympanic membrane on the outside, an inner ear structure developing within the neurocranium, that otic capsule region, and between the tympanic membrane and the inner ear we have this connecting bone, the stapes, there. So there's only one middle ear bone then in something like a frog. The final position of the hyomandibular, the stapes, right here. It's now connected to the incus and the malleus. The incus and malleus derived from the palatal quadrate and Meckel's cartilage elements here, and we're going to look at that next to see that transition. Now we saw how the stapes came from hyomandibular. Now we're going to look at how the malleus and incus are thought to be derived from the palatal quadrate and Meckel's cartilage. At the very back corner of the jaw in most reptiles, a lot of fish and amphibians, there is a bony component known as the articular, derived from Meckel's cartilage. Also from the palatal quadrate, the old upper jaw of the shark, we see the quadrate reduced to a little squarish, that's why it's called quadrate, squarish kind of bony member at the back of the skull. That's the point of articulation with the lower jaw. So our lower jaw connection is between the articular cartilage or bone and the quadrate bone in there. Part of Meckel's cartilage, part of palatal-quadrate involved there. And this picture right here is of that same lizard skull we saw earlier, the monitor lizard. Now here's a view of the articulation of the jaw in a human. The mandible makes up the entire lower jaw. There's no articular bone here. And instead of having a quadrate back here, articulation is with the temporal bone. Just a depression in the temporal bone here. So between the mandible and the temporal is where we have our jaw joint in modern mammals. That articular and quadrate component is thought to have moved into the middle ear series to become malleus and incus in the middle ear.